Okay, we're starting up. Any questions before we begin? Everything is A-OK. Goody, goody. Then today I'm going to continue a little bit with these different numerical schemes that we may choose, and also find out why we choose. So yesterday we talked about the advection equation, linear advection equation, and found out there that the central scheme, which is supposed to be second order accurate, actually should be the best, can't be used. It was unconditionally unstable. It crashed no matter what we did. Second option then was the first order upwind scheme, which actually was stable but terrible. Shouldn't be used. So we are in a pickle here. We have some problems. Today we are going to look at a case, classical problem, one-dimensional problem, with now advection and diffusion. But we look at a steady state situation. So here we have a generic equation. Our unknown phi may be whatever you want. Normally, of course, is going to be a velocity. But there you see we sort of cheat. So we have a velocity here already. So we have sort of linearized this term, keeping this velocity, the little u, as a known given thing. We know him. And let phi be whatever he wants to be. Using phi as an unknown is quite normal in such generic equations. Furthermore, for this problem here, then they have a diffusion coefficient, a big gamma. This is due to the fact that it is a generic equation. We haven't told what this phi is. If phi is going to be a velocity, as it's going to be in the end, of course this gamma is just the dynamic viscosity of the fluid. But since they have kept it this generic way, then they're operating with something called a Peclet number. Now you can just as well exchange that one with the Reynolds number. You see the Peclet number, non-dimensionalized density, velocity, and length, the length of our problem in the x direction, divided by this diffusion constant. And yes, if the diffusion constant then is the viscosity, then you see this as a Reynolds number. So you can think of the Peclet number as just the bulk Reynolds number. The problem at hand is a one-dimensional thing. And yes, we keep gamma, or the viscosity, constant. Density is constant, and the velocity, little u, is also constant. So we know them. And then it turns out that how will this phi change over a length L when we initially have given him a phi 0 and a phi L at both ends? If you don't have viscosity, then Reynolds number is 0. It's not defined actually. Then you'll get a straight line. It's pure transport. Only this term equal to be 0. But if you have viscosity, then you may get it something like this, with a positive Reynolds number. Negative Reynolds number here is a little bit awkward. We choose the little u here as a positive thing, then of course the Reynolds number is going to be positive. And it turns out the higher Reynolds number you have, the sharper is this shoulder here going to be at location L. We have an analytic solution for this problem, so we have something to compare with. So that is quite nice. Now we are going to solve this one using a central scheme and a first order upwind scheme. We can actually look at the result first. Let's see now. Here we have a problem of this one. So I've chosen Reynolds number globally as 50, and then just choosing 1 and 1 for all the unknowns here, and the length is 1, and I only have 11 nodes, so it's quite crude. But if we now look at the solution, we get something like this. We have the exact solution, that's the dashed line. This is what it's supposed to be. And then we have the central scheme, the blue one. He goes totally berserk, really oscillating. So not a good solution. The first order upwind scheme, well, he has a solution, actually quite far from the exact one, but it's nothing over and undershoot there. So this simple problem still is not easy for a central scheme, and the upwind scheme is also actually quite bad. So we are going to have a look at that one. So we have advection and diffusion, 1D. And then the equation at hand looks something like this. You have an x derivative. You can actually use ordinary differential here because it's only changing in the x direction. You don't need partial. And we had rho, we have the velocity, and our unknown. Equals, and then on the other side we have something like this, d dx of, and then we had this gamma, which I now just replace with the viscosity, and then derivative of our unknown phi, like that. And now we do it very, very easy. We say rho u, and the viscosity is constant. Then what kind of equation do we get? Well, then of course all our constants can go outside, and then you can push them on the other side actually to the well, let's keep them there where they are for now. It really doesn't matter. Let's see now. We have rho u, and then I have phi derivative. We can actually use an ampersand for derivative here. Equals, and then on the other side viscosity, and then double derivative, and then nothing more. So there you have it. Let's now create a central scheme and an upwind scheme for this one. Central scheme, central differentiating scheme. Well, here we have first order derivative. So if we have, say, a space here, x, and you have a point here, of course you just use the neighbor points, I minus 1 and I plus 1. To create a derivative, then I choose these 2 points and divide it by the distance between them, because I want it for the central point here. So the central scheme should then look something like this, rho u, and then I'll have phi I plus 1 minus phi I minus 1 divided by 2 delta x. So here I have 1 delta x. And then on the other side, you get the viscosity and then a double derivative. That one we create with central scheme, I plus 1 minus 2 times the center point plus the other point, minus 1, divided by delta x squared. There we have it. That one is second order accurate in space. Can be shown by looking at the modified equation, Taylor insert, around the center point, and then you'll easily see it. So no surprises there. But now let's rewrite this one a little bit. I want it on the form, say, in a way you would maybe program this one. You want to solve it. And then rewrite it on the form phi I equal to, and then throw everything else on the other side. Then what will we get? Let's see now. Phi I equals. Okay. We can remove one delta x, and then this last delta x go upstairs. This one goes down. So what do we have here then? We will have something like rho u delta x divided by 2 times the viscosity, like that. And then, well, actually this one then is negative. Yeah, we take that afterwards. And then we have the difference here, phi I plus 1 minus phi I minus 1. And then we have these two guys. Well, they are both negative. So we will have minus phi I plus 1 minus phi I minus 1. And then everything divided by or multiplied with minus 2. How can we do that? We divide by minus 2. Then I have isolated phi I. Let's see if this one is correct. Let's see now. What do we get? Well, first of all, here I have something. Density, velocity, and I have a length scale of my cell divided by the viscosity. That's also a Reynolds number. But it's not the bulk Reynolds number. It's a Reynolds number based on delta x. So people also call this a cell Reynolds number. So that's okay. So this one then equals rho u delta x by viscosity. Or in the example we had, they called it then the cell Peclet number, but it's the same. So yeah, that one we have right here. Here we have our cell Reynolds number. Let's see now, we have to divide by minus 2. So we should have something like, what will it be? 1/2 on the outside at least. The minus goes in. Then we have phi I plus 1. He's multiplied with what? Well, I have one of him here. And then I have one of him here as well. But now the minus sign is inside, so I will have minus cell Reynolds number half, like that. Then we have I minus 1, phi I minus 1. What's he multiplied with? I have 1 here. And then I have minus becomes plus, and then I have the same ratio here. Cell Reynolds number divided by 2. Here we are. So there I have sort of a recipe now, if I want to program this one. Making an iterative process. Of course, it's a very simple problem. You can solve it with a direct solver, no problem. But I want to write it like this because if you think in terms of stability, not any physical stability, we had to call it here numerical stability, then you have a very simple method finding out whether your scheme is stable or not. And it goes as follows. You add all the coefficients for all the neighbors. So here you see you have 1 minus this Reynolds number half and 1 plus Reynolds number half. The sum will be 2 divided by 2 equals 1. That happens very frequently, that the sum of all the coefficients becomes 1. If that happens, then you have one demand to make it stable. all the coefficients has to be positive. Well, for this coefficient, that's not a problem. My Reynolds number is positive. But you see this one, that's the problem. The cell Reynolds number has to be smaller than 2. That is sort of the stability criteria here. Cell Reynolds number has to be smaller or equal to. What does that mean? Remember, our problem is a steady state problem. We don't have the time derivative. But I still get some criteria here. And the criteria then will go for the spatial resolution. It's a demand for delta x. Delta x has to be smaller than something to keep this stable, if you want to use this CDS scheme. For the example that we just saw, I had chosen the bulk Reynolds number as 50. And now if you evaluate the cell Reynolds number, it's actually fairly easy. Let's see now, what do we need here? We don't need anything of this. And we don't need this. Any questions, by the way, before I remove it? Yeah?
The criterion that all the coefficients must be positive and add up to 1, what was that theorem called?
It's a sort of a stability method of positive coefficients, also called max-mean method. You can also see it if you write up your coefficient matrix here, and then you can have a look at this one, the diagonal dominance. So we have some rules there that the sum of the coefficients and so on, and the diagonal should be bigger than the sum of the others or equal, and so on and so forth. And here we violate this criteria if this happens. So that's another way to look at it. Other questions? Okay. Let's get rid of this. We don't need this one either. So I have my real Reynolds number. Then I had a length L here. But if you do it very, very simple, the Reynolds number equals rho u length by mu, and then you multiply this one with delta x by L, then all of a sudden you have your cell Reynolds number instead. And when I choose 50 and I had 10 delta x's, okay, then my cell Reynolds number is 5. Of course it's going to explode. So no way around that one. What can we do? Either reduce the cell Reynolds number by reducing the bulk Reynolds number, that's one way around it, or more cells. More cells. This criteria here is quite strict, actually, quite hard to do in practice. In many simulations you're going to have a cell Reynolds number which is quite big, bigger than 2. Then you're in trouble here with this central scheme. You can't really use it. You have actually another option which is not mentioned anywhere. You can take your original equation, steady state equation, and you add the time derivative, looking as a transient problem, and then just seeking the steady state solution. It's the same equation, you just have the time derivative in front. Then it turns out this cell Reynolds number has to be smaller than 2 divided by the Courant number, and then if you choose a very small delta t, you can make it work anyway. So introducing time, that's also an option. Keep that one in the back of your head. If you have trouble finding a solution with a steady state problem, simulate a transient and see if you can reach a steady state that way. That's normally a nice trick. Okay, this was the central scheme. Beautiful, but strict criteria. Okay? Now for the first order upwind scheme. the UDS. How do we find that one? Well, the scheme is going to be practically identical with one little twist, rho u, and when you create the derivative here for the advective term, you use the direction of this velocity. I said he was positive. Then I create a derivative upstream. Hence, I'm not going to use I plus 1, which is downstream. I'm going to change this ratio here with phi I minus phi I minus 1 divided by, and now one single delta x. But the right-hand side will be exactly the same. So no difference there. Okay, so now we need some algebra here. Let's see now. We have to rewrite this one a little bit. If I multiply up again here, delta x square and mu on the other side, we should then have rho u delta x by viscosity multiplied with the difference phi I minus 1, and then on the other side we only have these three, I plus 1 minus 2 phi I plus phi I minus 1, and then we can do it here. Phi I equals, so I have one here and I have one here. So let's throw this one on the other side. He becomes positive, so that should be okay. What will he be equal then? Well, I have something here. Phi I plus 1. Okay. Let's see, phi I plus 1. He is then multiplied with what? Well, here I have the cell Reynolds number again. I have to divide by that one. So it should read 1 over cell Reynolds number from that one. And what about this one? That's just minus 2, isn't it? But it becomes plus 2. Something like that. Then we have phi I minus 1. We have him, no, hang on. That was not correct. I only have one of them. He's not supposed to be there. Go away. I only have one I plus 1. But phi I minus 1, I have 2 of him. And let's see now. This one on the other side becomes positive. Phi I minus 1. He will also have this cell Reynolds number. Why did I divide it? Well, I had to, didn't I? Yeah, I had to. So yes, we will have 1 over Reynolds number here as well. 1 over cell Reynolds number. And then I have plus 1. This one on the other side. Shouldn't that be correct? Yeah, I think so. Something like that. But my phi I, he have what? I divide by the Reynolds number, and then I have 1 minus 2 over Reynolds number. So I have to write it like this. Divided by, should that be 1 plus 2 divided by the cell Reynolds number. There you have it. If you now use the same method, checking for iterative stability here, the sum of the coefficients, 1 over Reynolds number, and then 1 over Reynolds number plus 1, should then equal, well, we divide by this one, so yeah, it's 1. Beautiful. And then the next step was all coefficients positive. Yes, they are. Unconditionally stable. Unconditionally stable. There you have it. Unconditionally stable. You can do whatever you want. It will not crash. The central scheme crashes easily. Upwind scheme never crashed. Ooh, beautiful. We like that. We like that. But let's have a look at the price we pay here. Let's see now. We have our numerical scheme here. The left side equals, and then the right side. I'm going to need that one as well. So I'll do it like this. And remove here. Let's see, I don't need that one, no. Yes, I needed that one. That was the viscosity, thank you. Something like that. Yeah, we can simplify even further, can't we? We don't need this one, and we don't even need this one. So there we have just a scheme, okay? Find the modified equation. Insert Taylor series around the central point. I have one here, and I have one here. What do you get? Let's see now. For this term, I will have rho u delta x on the outside, and on the inside, I have the center point minus the negative Taylor series. How does a Taylor series actually look? Vi, if we take both of them, plus minus, then it will then be the center point plus minus phi derivative multiplied with delta x, and then it was plus, and then you will have delta x square half phi double derivative plus minus, and so continue with higher order terms. So what do we get here? Center point minus the negative series. So the center point disappears. This one is then minus, but we have minus minus, so he will become plus. So here we will then have delta x and then multiplied with phi derivative, which looks promising. Remember, looking at the modified equation, you're supposed to get your original equation back. So this looks promising. But I have another term here. Positive in the Taylor series, but it's negative here. So we have something minus. So let's see what we get. We have minus this one, delta x squared half phi double derivative, and then even higher order terms. So that was the left hand side. What about the right hand side? We have viscosity over delta x square multiplied with, we have 2 times the center point, negative, and then we have plus both series. Okay, both the positive and the negative Taylor series. So the center point is going to disappear. What about this one? Well, he's both plus and minus. He's also going to disappear. But this one, he will survive. I have plus both series, so I will have 2 of this guy, 2 times, and then we will have something like delta x square half phi double derivative. The third order term, he's going to disappear. One is positive and one is negative. So the next one to survive will be the fourth order, actually. And I will have 2 of him. Delta x to the power 4 half. No, not half. It's what is it, 24 or something? I think so. And then phi 1, 2, 3, 4, and then even higher order. So there you have it. Let's rewrite this one a little bit. Say we can multiply in here. What do we get? First of all, I get my rho u, and then I have multiplied with phi derivative. Beautiful. This one, let's throw him on the other side. What do we have then on the other side? 2 go by 2, delta x squared disappears. I have mu times phi double derivative. Beautiful. Mu phi double derivative. Looks very good. We have taken this one and we have taken this one. So yes, we have our original equation back here. We like it. But we have something else here. This one on the other side. What will he be? Well, he will be positive. And then we will have something like, let's see now, delta x squared over delta x. It should read rho u delta x divided by 2, something like that, times phi double derivative. That was this term. And then we have a final term here, something with delta x square plus delta x square multiplied with something which we don't care about. Okay. From this modified equation, here you can now conclude my scheme is consistent. If you take lim and let the deltas go to 0, you are left with your original partial differential equation, which you should. Consistent. The order of your numerical scheme, that's your biggest error. It's of order delta x. It's the first order method. If we had done the same with the central scheme, we wouldn't have had this delta x here at all. We would have a second order system. You can check for yourself if you like. But let's have a look at the double derivative on the right hand side. Let's see what's going on here. Need some more space here. Let's see now. I want to join these two terms. How do they look? So we have something called phi double derivative multiplied with, I have a viscosity, and then we have plus rho u delta x half, something like that. Okay. Take the viscosity and put it on the outside. Viscosity, double derivative, multiply with 1 plus, and what do we have here then? I have to divide by the viscosity since it's on the outside now. This is the cell Reynolds number, half. And there you have the price. So remember, for the central scheme, cell Reynolds number had to be 2 or smaller, or else he exploded. If the cell Reynolds number is 2, you see what happens here? You multiply this term by 2, meaning you have doubled the viscosity. Thank you very much. You are simulating a totally different fluid than you thought. And if the cell Reynolds number is big, 100, okay, then you have a viscosity 100 times what you thought you had. So that is the terrible price for a first order upwind scheme. You increase the viscosity. You add a lot of numerical viscosity into the schemes. Definitely illegal. Nevertheless, we can use it sometimes, but don't say it out loud, because it's a terrible, terrible scheme. First order upwind should never be used. So for this simulation here, as I said, I had chosen the bulk Reynolds number to be 50. And then he evaluates what is the cell Reynolds number. Yes, it is 5. Of course, it's going to be unstable. So what was the remedy? Well, you can, of course, change the viscosity here, but let's just increase the number of cells. Now I have not 10, but 20 delta X's. It helps. It helps. But still, our central scheme has problems. Of course, going negative here doesn't make any physical sense, so he's still unstable. The upwind scheme, unconditionally stable, but fairly far off what he should be, but never mind. So let's try then to increase even further. 31. Now we're talking. Now we're talking. 31, what is my cell Reynolds number now? Should be 1.67. Yes, it's under 2. And then also you can see the central scheme much better than the upwind scheme, much closer to the exact solution. Upwind scheme stable, but way off. And yes, you can continue increasing here, of course. Say if we go, what should we do? Oh, I can't plot this, it's going to crash. Never mind. We try 50. Of course, both of them are now stable indeed. But you see, you still get some deviation, quite strong deviation actually, between what you should have and this first order upwind scheme. So, as a conclusion here, if you can't afford enough cells, you're in trouble. If you have to rely on the first order upwind scheme, you can, but it comes at a terrible price. We have to find a remedy for that one. And that is more advanced schemes for this advection term. So we are then going to look at something called a total variation diminishing schemes. So here comes, say, the advanced advection schemes that we have available in open form. And some people say creating these more advanced advection schemes is the greatest achievement in CFD for the last 20-30 years. It's that important. And they are very good actually. We'll see how they work, but before we do that, then we are going to take a break. Any questions?